Yeah, so these are the numbers for the doubling of light on f-stops. So if you see a lens that is f4 max, and you see a lens that is f2.8, and you wonder why this one costs, you know, $300, and why this one costs $2,000, this has double. So this is a very abstract look at cameras and the way cameras work, and it seems one of those things that it just doesn't matter for the purposes of using a camera. But the nice thing is, from these basic principles, from these basic ideas, you can then extrapolate forward to why is this camera better than that camera? Why is this lens better than that one? Why does that person's photographs look like that and this person's photographs look like this? From the taking standpoint. Of course, you can mess with them as much as you want in Photoshop and things like that, but from in camera, this gives you some of those basics that you can then work forward on. You can also take some of these things and keep looking into them, right? Most of these things I have actually very much glossed over the functional scientific way it works in order to get it down to even the absurdly long time that this video has been running for. But realize that these are a super gloss over of these topics. If you want to know more, you know how to get to me. But yeah, this is super high level stuff. It is high level as in, like, it doesn't get down into the weeds, and it's gloss over of it, but hopefully that these words and these images kind of give you an idea of how the structure, how the internals of the camera work, and why some things are better than others. Big lens and our sensor. I have my distant object. We can put them at the same distance. Now what we're going to do is we're going to keep going through our sensor. Same thing here. Oh, I did not do this one right, but that's okay. Oh. Let's see if I can actually draw well today. Okay, so then if we come to some point behind our sensor, so an out of focus spot, right? An out of focus spot. Let's go to the same point. Our out of focus spot is going to be that big there, and that big there. Our out of focus spot is going to get much, much bigger. When we have this bigger aperture, our out of focus spots get big quickly, which for most people, this is what makes like wedding photos look fancy, is that they're shot on lenses that are very wide open with a lot of distance to whatever the object in the background is. And what that does is it makes the out of focus parts very out of focus, and it looks kind of dreamy in most images. And so that's one of the things that people really, really like in lenses with large apertures or low f-stops, right, because they're backwards. It gives you this really nice out of focus part. Now, we might as well just cover focus while we're here. Let's get some orange action. Now, if I have, as my markers attempt to attack me, if we have, let me push this guy out a little further. We have an object that is in focus, right? If I have an infinitely small point right there and I get an infinitely small dot on my sensor, that is in focus. Now, but if I'm focused here, then this is not going to be in focus. And this, let me figure out where I'm going to draw this. What this is going to be is in focus to the front. So this is going to go like this. Alright, so this is going to go like that, which gives us big out of focus spot for our image, for our object over here, right? We're getting this big out of focus spot. Now, if I move this backwards, right, or if I move my sensor up, think about it either way, I can get this orange object in focus, and I can put the blue object out of focus. So, the closer these two things are, if these two things are close to each other, then I will get to infinity focus. Infinity focus. That lets me focus out to the horizon, right? That lets me focus out on things in space. That lets me focus away from my camera. So the closer the lens and the sensor are, we get close to infinity. If they go far away from each other, we get objects that are closer. So for a macro camera, right, so for a lens that's meant to focus on things really, really tight, we actually push the lens away from the sensor, like way away from the sensor. There's actually things called macro extension tubes, and all the macro extension tube does is it just sets the camera, or sets the sensor and lens apart from one another. So we can focus just by bringing this in, by pushing it back, right? We push the sensor and lens away, we get closer objects. We push the sensor closer, we get more distant objects. So we can go from infinity to close, or macro, but macro is a specific word. Now, there's another thing that's going to happen here. We can increase the size of our aperture, right, the hole that our light is coming through, to get this really nice thing to happen. We can also increase the apparent size of the sensor. I'm not going to cover that, but just realize that the apparent size of the sensor is going to matter. Okay, now let's talk about the millimeter range of a lens. So we just talked about the f-stop, and just while we're on the little numbers that are on a lens, we might as well just keep going with this. You will see something that says, let's say 50 millimeters. I just talked about that with my little f-stop math. 50 millimeters. What does that number mean? That doesn't mean the length of the lens, right? This is a 35 millimeter lens. This is not 35 millimeters long. This is absurd. What this means how far is the lens from the sensor when an object at infinity, right, at infinity is in focus. Right, our perfect little focus spot, when an object at infinity is in focus, this distance is the millimeter range of the lens. Now, if this doesn't really help with what this actually does for our cameras. What this does for our cameras and what it does for our apparent use of those cameras is that the lens either looks thinner or wider. We can either see less of the scene or more of the scene. The longer this millimeter rate is, the longer this is, the less of a scene that we're going to see, right? We're going to see a very tiny little narrow angle of this scene. As we go wider, right, for wider lenses, we will get progressively more of a scene. Now, there are calculators that will transfer the millimeter rating of a lens to the angle of view, right? The field of view or angle of view. There are calculators that will translate this. The math is weird. I'm not going to deal with it today. It also depends on how big this sensor is. So just be aware that some things will say this many millimeters on this camera, or it will say 35 millimeter equivalent or something like that. It will say equivalency on there. And what that is giving you an idea of this camera looks like a full frame camera, or it looks like a film camera with that size lens on there, with that length of lens on there. Because most people are kind of used to that as a base measurement or as a spec for a camera. We can use that if we want. We can use the real thing if we want. Once you get really into this, you just kind of know how these things work, or you just ignore it and buy whatever you think looks good to you. So millimeter range of these lenses. This gives us the field of view angle. The lower this number is, the wider it's going to be on a full frame camera, which is that full frame sensor, which is 24 by 36, I think, millimeters. On that sensor, we have a range. I have lenses that are reasonably wide that are 15 millimeters. 15 millimeters is just, I think, 170 degrees ish, but it's very wide. It's a very, very wide lens. The long lenses that you can get are, I think the longest lens I have is 300, and that gives me about a 4 degree. Something like 4, let me actually look that up really quick. So 15 millimeter gives 100 degrees. This is 100 degrees. The 50 millimeter that we talked about over here is 39 degrees. Field of view, so you can kind of do that out. 45 degrees is, how big that is. Let's see, 300 millimeter is 6.9 degrees. Sorry, that was wrong. 6.9 degrees. And that's on the horizontal. That is this measurement horizontal. A lot of lenses will define themselves by field of view corner to corner, especially wide angle ones will define themselves as corner to corner field of view. So just be aware of that. Yeah, so millimeter length is just where this has to be to focus a sharp spot. The effective use of it is that it makes a lens shorter, which is wider, or longer, which is thinner. Another thing to think about when we're working with this is that as we increase this number, right, if I have our 50 millimeter lens, that's f1.4, right, f1.4, well, I want a 300 millimeter lens that's f1.4, right, so I want 300 1.4. Well, now we have to do the math. So 300 divided by 1.4 gives us 215 millimeters. So to have a 300 millimeter f1.4 lens, I would need 250 millimeters, about 8 inches. So about the width of this piece of paper, about the size of a dinner plate. So just be aware that as we increase this millimeter range, as we get thinner, to get our f-stops up, we need absolutely gigantic apertures and huge pieces of glass to go with it. And again, very sharp, very nice pieces of glass, because we're doing a bigger area and we're making a bigger aperture. So we must be careful about that. So that's why you can see, if you watch like basketball or football or something like that, and you see all those giant lenses on the edge of the stadium, those are lenses that are very long, that are also very high aperture, which gives you these dinner plate front ends on these lenses. So just be aware that that's why they look so huge. That's also why they're freakishly expensive, but that's why they look so big, is that when you're at this length and you need a bright lens, well, now the hole we're shoving light through has to get really, really big. A little more on millimeter range lenses. For a simple one lens system, again, the distance between the lens and the sensor, that's how far we're at. We can think about this, and I want you guys to have a real understanding of this, is that the longer focal length of a lens, we're really just cutting down on how sharp of an angle our light makes when it hits our lens, right? We're just cutting down on this angle. If we want a longer focal length, right, a longer distance from the center of our lens to our sensor, the way we do that is we go with progressively flatter lenses. So the way we can kind of think about it is an ultra wide angle would essentially just be a sphere, right? Sitting right on our sensor, the light comes in, come in from a point, and it would focus onto a point. An ultra-wide would essentially be that. Longer lenses are going to be progressively smaller portions of that sphere. Right? So if I have a spherical lens, smack it up on there, half, we can get a focal point sometimes. But for longer lenses, all we're doing is we're taking progressively less of this shape. Right? So if we make a lens out of this shape, that gets us a lens that's still pretty heavily bowed. Then if we take a lens out of this shape, we get a much thinner lens, and we can progressively take thinner and thinner slices that give us longer and longer focal lengths. So just realize it's nothing fancy. We're just taking progressively thinner slices of a sphere. There are aspherical lenses which can do some fancy things, but for the most part, this is what we're looking at. There are two words that are kind of important words. One of them is telephoto. 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 Telephoto is any lens, and we got to think. I've been drawing lenses as single lenses, but lenses are really these, fancy, expensive tubes with lots of lenses in them. Right? We have all sorts of goodies in here. In these lenses, a telephoto lens is a lens that has an effective length to sensor that is actually physically longer than the body. So this could be a 300 millimeter lens that is only actually 150 millimeters long. And what you're doing is you're using the multiple lens elements to bring that tighter faster, to get you to a focus point quicker than you could with one. The other thing is literally just the opposite, and that is retrofocal. And a retrofocal lens does the opposite thing. A 12 millimeter lens, that's pretty small. 12 millimeter lens from the center of the lens to the sensor, that's actually about 12 millimeters, right? About the width of my finger. There's no cameras like that cover a full frame sensor, or 15 millimeters, is right there. Still, there's no way we're going to get a sensor, or there's no way we're going to get a lens in there that can cover a 35 millimeter wide sensor. It's just going to be absolute craziness. So what we do is we have something called retrofocal. So instead of using all these lens elements to reduce this value, we use a number of lens elements to extend this value. So by using these multiple lens elements, we can actually extend that value and get wide-angle lenses that sit further away from the sensor. And you probably won't ever hear this word, but it's important to know that a 300 millimeter lens does not have to be 300 millimeters long, and a 15 millimeter lens can be a whole lot longer than 15 millimeters, and it is because of these two capabilities of lens design. So just realize that the length of the lens doesn't matter. It does to a certain extent, but it is not the end-all be-all. Oftentimes we can do these fancy things to avoid situations that are just physically impossible, or so gigantic you would never want to carry it around. So that's telephoto, and that's retrofocal. So let's talk a little bit about lenses and how light moves through them. We have our lens, and we've talked about light coming through it in a very linear way, without much issue. Now light doesn't do that. Light does horrible things when it meets a surface. You guys have probably seen Prism. All the light will come in at the same angle, then leave at different angles. What does that mean for a round surface? Right? We have, let's do it here, erase a little bit. And the reason I want to cover this is because it covers a lot of why camera lenses are so expensive. It's not just one piece of glass, it's a handful to dozens of pieces of glass, because not only are you trying to make this happen, sharply, but you're actually trying to make this happen as well. Let's say we have a white light, right? So even amounts of blue, red, and green. We are going to have a red that bends less. We're going to have a green. Let's go the same way, right? We're on the same path. We're going to have a green that bends a little more. Now we're going to have a blue that bends a lot. I think you can already kind of see the problem here. Blue is focused here, green is focused here, red is focused here. However, we can use different kinds of glass with different chemicals, treating both faces, to bring these colors back together, to bring them so they all line up on the same part. That's what's referred to as crown and flint glass, is the two that are the old school ways to do it. But that will bring these back together so all of these line up right in the same spot and make a position right there. One thing you'll see is that, again, lenses will not be like this. It'll be 5 lenses in 4 groups, or 12 lenses in 6 groups, or 12 lenses in 9 groups. All that means when you hear those words is if I have 5 lenses in 4 groups, that just means that one of the lenses is 2-part, right? We have one lens here, we have one lens glued to it, and then I have 3 separate lenses that are not touching. So this is 5 in 2 groups. I could have 5, I'm sorry, this is 5 in 4 groups. Let's see if I can keep this consistent. 5 in 4 groups, right? That's one group, 2, 3, 4. I could have 5 lenses in 2 groups if I had there's some lenses that do that. If I had something, let's say like this, right, where I have a triplet, which is 3 lenses stuck together. 5, and let's say I have a doublet, which is 2 lenses stuck together, right? Double, 2. Say I have a doublet like that. So there's 1, 2 glued together. This is 5 lenses in 2 groups. This totally doesn't matter unless you really get into lenses, but it does make a difference in how much light comes through the camera and the way that the light comes through the camera. If you have a lens that is, let's say you have 2 50mm lenses. You have 2 50mm lenses that are equally sharp. One has 10 elements, one has 5 elements. 2 lenses that are equally sharp, 50mm. One has 10 elements. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. One has 5 elements. 1, 2, 3, 4, 5. Right? This is very rarely going to happen, but let's say we have equally sharp lenses 5 and 10. Now, every time the light goes through these, we saw that the light will bend as it goes through these. It will also reflect to a certain amount. That reflection takes light away from our source here, right? If we have our light here and it goes through here, every time it bends and it bounces a infinitesimal 1% back. Well, if we bounce 1% back progressively through this, that's like 15% of our light loss, and because it's progressive, guys, it's not just it's not added, it's multiplied. But that's a huge amount of light loss versus this fewer number of elements. So by having fewer elements in a lens, we can actually increase the amount of light that gets to here. It's just much, much harder to control for the color splitting, to control for all the other things that we want to control for in a nice lens. But realize that greater numbers is not necessarily better. Sometimes there are low element count lenses that do exactly what they're supposed to do. So if you see a high element count, that doesn't necessarily mean it's a better lens. Might be a better corrected lens, but it's not necessarily better and will almost always be a darker lens for the amount of light that is transmitted end to end through that thing. So just be aware that when you see these numbers, they sound super fancy. It just means how many chunks of glass stuck into how many groups, and if you have too many, it starts to knock down the amount of light. So just kind of be wary of this when you're looking at those things. These numbers do matter, but they're not going to matter for a lot of what you think they do. Alright, so for a lens, gone over pretty much everything in a lens. So what we're going to do now is just kind of reiterate what those things are and kind of what you'll expect to see on a lens. The first thing you see on a lens is the millimeter rating. The millimeter rating of that lens. That is how long the lens is. A bigger number here is going to be a tighter lens. A lower number is going to be a wider lens. And these values, again, are relative to the size of the sensor that you're putting your lens in front of. So do be aware that these values change depending on the camera you're putting it on. There are a few classes of cameras, and within that class all the sensor sizes are the same, so it's not like everybody's got their own sensor size, which is nice. The other thing we will see is X millimeter, let's see if I draw M's, X millimeter equivalent, and that is to make it so everybody knows what you're talking about. It is what this lens looks like on that sensor. This does not work at all for the size of our bokeh, right? The size of our out of focus areas. It does not work for that element. It doesn't work for it at all. So realize this is a field of view equivalent, right? It's a field of view equivalent. It is not a out of focus or depth of field equivalency, right? The depth of field is that area that gets tight enough that we think it's in focus. It is not either of these. That's a no-no. The X millimeter equivalent is only for field of view. This is a calculable number. There's calculators online to do it. We're not going to worry about it here. So realize we have lenses. There's X millimeters. The next thing we're going to see is that f-stop. We're going to see f x point x. Remember, the lower that number is, the bigger the hole we're shoving light down, and the brighter the lens is, it's also going to be more expensive because the glass has to be better. The glass is going to be bigger for both of these reasons, right? This number gets bigger or this number gets smaller, we're getting bigger, more expensive glass. So we'll see our f-stops there. The brightest thing that you will normally see on a lens is 1.4. The dimmest or the least bright you'll see generally is a 5.6. Sometimes you'll see higher than that, and you can always make an aperture go higher than that, but at its maximum, very rarely are you going to see anything darker than 5.6. You will see silly things like in Spielberg, it was when they shot Barry Lyndon, they shot that on a f.75 lens, which is I think 2.5 stops brighter than 1.4, so it's very bright, very silly lens. But just realize that these numbers, the lower they are, the bigger the hole we're shoving light down. Get rid of this real quick. When we're working with millimeter ranges that change, sometimes you will see, let's say, like 18 to 200 millimeter. Right? That's a zoom lens. That's a lens that can change its effective focal length. So we're changing our effective focal length. When we see lenses like this, we will often see f numbers. Let's say this could be f 2.8 to 5.6. This just means that our f-stop is going to change as we go up. So if we're at 18, we can get f2.8. At 200, we can get 5.6, and then everything in between these is going to be something in between these. So realize that these are not absolutes. We can sometimes have ones that zoom. We can also have constant aperture zooms, but those are usually pretty expensive. And a constant aperture zoom will just be the same thing, except it just doesn't have the second number. It'll be 18 to 200 f2.8, but very, very expensive. Excuse me. Other things we'll have is whether or not the lens can autofocus. That makes sense. You're either manually choosing your focus, you're manually moving the lens in and out to get your focus, or the camera's doing it by itself. Pretty much every camera you've ever used is probably going to be autofocus, just because it would be very silly to have a manual focus lens on a cell phone or something like that. So autofocus isn't really a thing anymore because pretty much everything is autofocus. Only older lenses are going to be manual focus or specialty lenses. Some specialty lenses can be manual. Another thing you will see is a symbol that looks like that, and that is just diameter. That's the diameter of the little piece of glass that goes on front to protect the lens. You can get a nice little screw-on piece of glass. There's actually another piece of glass on top of this lens that screws on, and what that symbol is, and it will either be straight up and down or like this Sony is, it'll be at an angle, and it'll be some number. That's just the diameter of that piece of glass, and then you can go on Amazon or whatever and just buy that piece of glass that fits that. If you buy the wrong size, it will not fit because there's screws in there. So realize that if you see this little symbol, this is just diameter. It's just the piece of glass that goes on the front of the lens. It's not really terribly important to the quality of a lens. The aperture, right? We've talked about the aperture as the number, the size of the hole, right? But we also want to go back and think about the blade count. How many blades do we have is important. So when we're thinking about a lens, that's another thing that I find important. It really depends on what you're looking for in a lens. Alright, I think that kind of covers us for what you're going to see on a lens. You're going to see this millimeter count, you're going to see an f-stop. You're not going to see this, you're going to have to look this up. This is also going to be on the front of the lens. Yeah, these are the basic things. Just realize that f-stop, that number gets lower, the amount of money gets much higher. If the millimeters aren't quite the same. Millimeter range, if you're anywhere from, on a full frame camera, anywhere from like 35 to 85 is pretty cheap, right? This is the lowest amount of money you're going to spend for an equivalent f-stop. The longer you go and the shorter, i.e. wider you go, the more money you're going to be spending, right? So just be aware that the millimeter thing is different. F-stop, the lower that number is, the bigger that hole, the more money you're going to be spending. For the millimeter count, it's not the same. There's actually a sweet spot that's relatively easy to design lenses, and then it's very hard to design wide lenses, and very hard, or they're just big pieces of glass for your longer lenses. So just realize that the amount of money that you're spending on this is because of some combination of these things. Now that we've covered lenses, let's move on to the sensor, which is that back part of our eye. That's the part that actually gets light. We have our basic shape, we have our lens, we have our eye, and then all the sensors were the things that dot the back. Now, of course, in a camera, it doesn't work like that. We don't have organic sensors. We can actually do all of the stuff with a camera with just a white sheet of paper. With a long enough lens, you can just have the lens here, the white sheet of paper, and you'll just see a projected image of the outside world on that white sheet of paper, assuming your object is bright enough that you're photographing. So that is what's called a camera obscura. That is just the lens, the box, and a white sheet of paper on the back, or light colored sheet of paper on the back. And that will give you a camera obscura. Now, people use that for a long time because you can put a piece of paper in there and then you can trace your image, right? If you project the image, you can trace it. This is a very easy way to get good proportions on people, to get perspective on buildings and things like that. So we can actually do all the stuff we've been talking about so far with just a lens in a box. You just have to look at it as you're taking it. You don't get to keep it. You just see it. Not very useful for most of what we want to do and what people want to do in general, right? You want to capture the image and keep the image. So what people did is they realized that there are some chemicals that, when exposed to light, harden, solidify, change chemical structure, however you want to say it. I'm not going to get into the chemical photography part of this because I just don't really know that much about it. I've always shot digital. So once you have your piece of film, you then expose it, and exposing it is just taking some sort of shield, right? The shield can actually be on the outside too. A lot of these older cameras, you literally just take the cap off, count until you're done with your exposure, and then put the cap back on. Modern cameras have a shutter in here. Before we move on to the sensor, let's just do the shutters really quick because it just shouldn't take that long. Some of the shutters now are actually part of the sensor, but older shutters are not. There's a few kinds of older shutters. The easiest way to do an older shutter is you actually have little plates. Now what you do is you just scissor all those plates up, and then you actually bring another set of plates in from the bottom. You don't open them this way and then close them this way. You actually open them this way and then bring a completely different set up from the bottom. Now, why might you do that? Right? Why might we do that? This seems so much easier. This seems like a pain, right? You have to have two sets of these shutters going up and then the next one coming up following it. Well, if we do this, let's take a few samples on our sensor, right? We have our piece of film or sensor or whatever that we're taking our image on. Now, in the first second, this is open. Closed, 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 right? And then as we bring this up more, this one and this one is open. Then this one, and then this one, and then this one is open. Then all four are opened. Then if we try to close our shutter back the other way, we get 4, 3, 2, 1. So what's going to happen is the bottom part of our sensor or piece of film is going to have 1, 2, 3, 4, 8 units of light. This one's going to have 6, 4, and 2. So we're going to have a really dark top to our image and a really bright bottom. Well, let's see what happens if we do our 4 levels again, but we open it this way and then we close it with a following shutter. Well, we can do that. We open it again, we open it some more, we open it the 4th time, and then our bottom shutter starts coming up, so we only get 3, then we get 2, then we get 1. So now if we add all these together, we have 4 units of light, 4 units of light, 4 units of light, 4 units of light, and these are all the same, right? Top to bottom, we're getting the same amount of light across our image. So we do need to have a shutter with a second following shutter. So these follow one another. If we went up and then back down, we would get this and it would be terrible. So instead of doing that, we are going to get the we are going to get the shutter that goes up with another shutter that goes up following it, giving us even amounts of light all the way up our sensor. Much better way to do it. These shutters move too fast to really see what happens when this is happening. Just to give you an idea, modern cameras have about 1/300th of a second. So from the first shutter starting to come up to that second shutter finishing is about 1/300th of a second. But you say, my camera can shoot faster than 1/300th of a second. I can go to 1/2000 or 1/4000th of a second. If I can only move this, top to bottom at 1/300th of a second, how in the world am I doing it in 1/2000th of a second? Well, so that's reasonably easy. Instead of letting our shutter get all the way open and then starting to close it, what we do is we start the shutter opening, and then almost immediately afterwards we start the shutter closing. So instead of getting 4 units of light like this, what we're going to do is we're going to get 1 unit of light, right? Our shutter started opening, but then I'm going to start closing it. So then we only get 1 unit, 1 unit, and 1 unit, and then the shutter's closed, right? Because our second shutter is blocking our way up. So what this allows, this makes it so we can get a shorter shutter speed than the movement of our shutter. But realize that this light at the bottom of our frame is actually happening at a different time than the light at the top of our frame. The light at the top of our frame is actually a little bit after the light at the bottom, or the other way depending on which way your shutter is going. So do realize that shutters faster than this, right, all the ones above whatever your shutter speed is, do not have a point in time in which this whole plate is open. They are essentially moving along as a plate up the image. There's another kind of shutter called a leaf shutter, where instead of having all the flat plates going this way and moving, up with the follower, what we're going to do instead is we're actually going to make something that looked a lot like those aperture blades. So instead of the aperture blades closing down from a big circle to a small circle, they're going to go from a big circle to being completely closed. And so by doing that, all they do is they open and then close. And with that, the nice thing is you don't need followers. They can just open and close. So these can do some very interesting things. You can have flashes go off at different times during the exposure. You can do some, let's just say you could do some fancier things with lighting, especially very, very fast light. But they're very expensive and very rare. If you need one, you probably know you need a leaf shutter, and you shouldn't be watching this video. Yeah, very expensive, very rare, but can do some very fancy things with fast light. So that is leaf shutters. The other thing we can do, and probably actually what most of the cameras that we have will do, is something called an electronic shutter. So an electronic shutter just uses those sensors. So those sensors are all going to read out, let's just say there's a grid of these. I'm not drawing a grid. Too lazy for that. There's a grid of sensors. As each line takes, it will leave this line open for a certain amount of time and available to light. And by available to light, I mean electrically available to light. There's nothing physical moving in front of it. When your phone makes a camera sound, nothing's actually moving. It's just faking that. So it leaves this open for a certain amount of time, leaves the next one open for a certain amount of time, and it reads that data down in order. So it reads this data in order. So it would leave this one open and then read the data down. And then as these are left open, it will progressively read them down. There's another type of shutter, which we'll get to when we talk about sensors, which is called global shutter. And it does the same thing, except all of these open at the same time, and all of these read at the same time. It's called a global shutter. It's going to be the next big fancy thing in probably about 5 years. It's what I'm waiting on for cameras. But so yeah, so instead of reading line by line by line, global electronic shutters will read all of the pixels at exactly the same time. So there's some advantages there in regards to speed. Now, let's talk about speed of shutters really quick before we move on to get really into sensors. Speed of shutters. Your eyes don't have a shutter, so there's no relative thing that I can say that's the way your eyes work. The shutter speed that most people can handhold a camera at is 1/50th of a second. 1/50th of a second is about what most people can handhold a camera that's got a normal lens on it and shoot a clear, still photograph. If you go slower than that, you're probably going to get some blur in your image. Or if somebody's moving really fast, you're going to get blur in your image. Then you can go faster than this as well. You can go up, I think my camera tops at 1/4000th of a second. Most cameras are 1/4000 to maybe 1/8000th. 8,000, not 800, 8,000. Somewhere in that range would be the maximum. You can get cameras that go faster than this. It just depends on what you're doing with them. If you get cameras where it really looks like where all like the water starts to look like jelly and things like that, you're probably in this 1/2000, 1/4000, 1/8000th of a second. sort of range, very, very fast range. Another way to think about it is if 1/50th is too simple, 1 over the millimeter number on your lens, and this only works for full frame cameras, but 1 over the millimeter number of your lens gives you about what you need. So if I have a 300 millimeter lens, I'm going to want a 1 over 300 exposure so I'm not blurry. I find this too slow, but I have shaky hands, so if I'm using my 300, I shoot at 1/1000th of a second, just because it's not a super bright lens, and I need, my hands are just too shaky to do that. So realize 1/50th of a second is about what most people can hold for a normal lens. 1 over the millimeter number is the same as that, just for other lenses. Fastest is going to be about these. Now slower is going to get you that blur. If you want to go slower for effect, what you need to do is put the camera on a tripod, right? Put the camera somewhere where it's still, right? This camera that I'm using right now is up on a tripod. I can move it, see? But generally it's very still. If you want to go slower, put the camera on a tripod. Then you're going to get blur in things that move. So you can get like a waterfall that looks all misty and looks very like fantasy. And that's going to come from these slower shutter speeds. And those slower shutter speeds on most cameras go down to 30 seconds. But there's a mode called bulb. And bulb is literally just as long as you hold down the shutter button, it's going to keep taking the picture. Once you let your finger off, it will take the picture. Or it will stop taking the picture. It'll bring up the second shutter. So that's shutter speed. The only other thing to really think about with shutter speed is that these are going to be relative to f-stop and aperture. This is going to be relative to f-stop and something called ISO that we'll get to when we get to sensors and when we come back and bring them all together. But realize that this is what most people get handheld. That's fastest. These are slow. And realize that the speed of this is how much light comes into the camera. So not only does it affect the way the image looks afterwards, but it's also the amount of light, right? If I'm standing out in the rain for 10 seconds, I get 1/3 as wet than if I'm standing outside for 30 seconds. So you have to think about the photons coming into our camera, right? We have little light chunks coming into our camera, and the longer I can keep that door open, the more of these I'm going to get in. If I have to, open and close that door really, really fast, I'm not going to get many of these in, so my image is going to be darker. So do be aware that it's not just the speed, but the faster we go. If I take a 1 second image, and I take a 1/4000th of a second image, this is going to be 4,000 times less light. 1,000 times less. That is a lot less. That is way, way less than this one is going to be. So be aware that when you're shooting up here, you need an absolute lot of light to shoot comfortably at these higher speeds. Alright, so it's very quickly shutters. Alright, now let's get into sensors proper. Again, we have lens, dark space, our eyeball. We have our sensor plate. Again, it's going to be film. In older cameras, it's going to be a camera Obscura before that, or now. You can still make camera Obscuras. But in our case, what we're interested in is this as a digital sensor. Our back plate, our thing that senses, is a digital sensor. Important starting place. A digital sensor is made up of individual pixels. So if we look at the face of a sensor is going to have a grid of individual pixels. Of course, there's going to be many, many more than this. For example, this is 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. So this is 24 pixels, right? There's 24 individual spots where light can hit, and it will take in that information differently. Most of your phones and or cameras are going to be somewhere in the 12 to 36 megapixel range, and megapixel just means million. So your cameras are 12 to 36 million pixels. This is 24 pixels, not millions, not anything. So realize that the cameras that we're using have a very, very high megapixel count. It's many thousands on each side of our sensor. Let's start a little bit older. There are two major kinds of digital sensors. One is a CCD and one is Cmos. These are types of integrated circuit, essentially. This is a charged coupled device. It stands for charged coupled device. These can do some very fancy edge case things, but are pretty much not used anymore. Older DSLRs use these. They can have very good low light performance, but they have a lot of problems, and they do very poor when they have to repeatedly take images. So for things like video, they're just almost completely out. And then there's Cmos. Cmos is what pretty much everything uses now. It's cheap, it gets the job done. It used to not be as good as CCD, but I would say maybe 5-10 years ago it got parity and got better. And it's just better for a bunch of other reasons. Cmos is complementary metal oxide semiconductor, and that doesn't really matter for our purposes. Again, a charge coupled device doesn't really matter for our purposes. One of the big things that's different is that for a CCD, all of these pixels are sensors, and then there's an amplifier over here in the corner, and we shove our signal to the amplifier, let the amplifier amplify it. That's just like turning up the volume on your stereo. We let our amplifier amplify it, and then we read out that information. For a Cmos, we actually have amplifiers on each pixel. So each pixel is going to have its own little amp, and then it's going to read out that information to the end of the line. Right? We're going to go to the end of the line, and then read out each line in order. But each one's got its own little amp. CCD has one big amp. Generally, there are totally exceptions to this, but generally that's going to be the biggest difference. This was able to get better low light performance. This now, with advances in essentially in microcircuitry, is now better just through essentially brute force. But it is different, and it does matter for very exotic things, and actually just older things. If you buy a camera that's 15 years old, you could actually get one with a CCD. And in some cases, I actually like the color from a CCD more than the color from a Cmos, but that's a completely different conversation. So in there we have some other interesting things, in that in each of those pixels, right, each little pixel actually cannot sense color, right? We have cameras that can take pictures that are in color, but each little pixel actually can't sense color. They just sense visible light within the spectrum. They can actually sense some things outside of visible light, and that causes a whole slew of other problems. But this little sensor cannot detect color. Can detect light all day, cannot detect color. So we want to get an image in color. Well, the best way we know to do that is let's just replicate the color we already used. Sorry, I'm doing these out of order for people who have issues with that sort of thing. Let's use those colors that our eyes see. We have red, green, and blue. So the colors that our eyes see. So let's just go with those. They're split enough that it's relatively easy to see. So what we're going to do is that we have this thing that cannot see these colors, but we need this thing to see these colors. So let's look at it from the side. We have our sensor layer. Let's get a few of these sensors out. Let's get 3 of them out, actually. We have 3 sensors. These go off to tell a computer, hey, I've seen light. Hey, I've seen light. Look at me, I've seen light. And let's say we want them in red, green, and blue. So to get this sensor to see red, can't see color, to get this sensor to see red, what we need to do is put a blue filter and a green filter. My pens are invading again. Blue filter and a green filter. And then in the next one, this one, we're going to put green. Let me just go ahead and draw all of these. I'm missing one. There we go. So, if we have all three colors of light, markers are being recalcitrant. We can see that green light is not going to stop at the blue layer. It's not going to stop at the red filter. It's going to get all the way through. So this one in the middle is going to read green. Same thing with this. The red is going to get through. Red is going to get through that blue layer as well. Get to our sensor. This is going to give us red. Right? If I try to get red light in here, it's going to get through. It's going to hit this red filter and then stop. So we get our pure green. Same thing with blue. Blue goes through. Blue goes through the green filter, gets to our sensor, and that gives us blue. So we have this pattern, red, green, and blue, and this is how we're getting it. Now this has big problems because we have blue light, green light, and red light. Sorry, green light. And we have red light coming through here, right? We have three colors of light that make up the white light that we see. Every one of these sensors is throwing away 2/3 of that, right? 2 out of every 3 photons that hit this, if we're seeing a white surface, we're just tossing it in the trash. So this is a very inefficient way to do it. All the cameras you've ever used, except for a few, we'll talk about those, throw away 2/3 of the incoming light. Just right in the garbage, thrown away. So they're not very efficient. This is just the best way that we know to do it right now. So this is the way we do it right now. There's an interesting thing. You would expect that when we go to multiple pixels, right? Let's say we go to multiple pixels. You would expect these to be in even quantities. You would expect it to be red, green, and blue, and then maybe a different pattern, but red, green, blue, right? You would expect it to show up kind of like that. But that's not the case. If you remember right, we had a little chart. We had a little chart of the visual spectrum of the human eye. And red was the slowest. Green was the fastest. Blue was the fastest. Green is right over near red. And then we actually had a different fellow. We had the rods in our eyes. The rods in our eyes were something like that. Now when those rods, this green, red, blue, well, if we're just doing red, green, and blue pixels, and we're doing them evenly, if we're adding this, and this in even amounts, we're actually going to get a shift in color this direction that we're not going to like. So what these sensors actually do is they have green, red, and blue. Or you can, of course, switch these. So you could do something like, this is actually probably the most common one, is red, green, blue, green, red, green, blue, green, red, green, blue, green, all the way along. And then the next line, let me get rid of that. So this would be greens here, and then this would be greens here. So what you want to do is not have these in vertical lines. So you'd actually offset your colors like this. So you'd have a screen that when you cut it up is actually half green. Now you look at this, you say, this is nuts. Why did you do this half green? It doesn't work at all. But if you look, our rods and the green is very close together. So the rods in our eyes that see something very close to green, and the cones in our eyes that see green are very close together. So we can fake that by just doubling up on our greens on the screen and on the sensor, and by doing that we can fake for humans having this other non-color that exists right here in the rods of our eyes. So realize that these are not even. There are two greens for every red and blue pair. It's always one of these. There's a few other patterns of this, but this is the most common one. So yeah, so realize that these are not even. There's double the greens because that's the way, or it's not the way. It's very close to the way that our eyes see, so it's an efficient way to do that. Now, having these filters like this causes some problems. Each of these filters has some thickness to it. Each of those filters has a little bit of thickness. So if we think about these sensor stacks, I'm going to overdo this a little bit. We have our piece of green glass that filters green. We have a piece of blue glass that filters blue. And then we have our sensor that can see red, right? We're just going to make this a red sensor. I know it's purple. We want to see red. Now, this is all in a little house, right? This is in a hole, because if we just had these lenses right next to each other and there was another lens right here, then what would happen is that light would hit this, especially if it was coming at an angle, and then scatter sideways through this lens, and we would get very, very fuzzy pictures, and we would not like it at all. So we don't do that. We put these lenses down in little holes. Now, there's a big issue with this. As I said before, we have a lens, we have a sensor. If our lens is very close to our sensor, and we're focused on this object, look at the angle that this is coming in at. That angle is coming in like this, right? If this is the flat of our sensor, this angle is coming in real, real hard. So if I have this color come in at this angle, even with a little bit of tilt, I get a huge shadow on my sensor, right? I only get a tiny, tiny little speck of this red compared to what I would get. You know, if the light's coming this way, we're set. There's no issues at all. No issues at all. But if the light comes at an angle, as in lenses that are very close to their sensors, this creates a huge problem. These nice walls that we built to keep our sensors very sharp are now all of a sudden keeping our light from touching our sensor. Come straight on, we're fine. The edges can cause problems though. And for those of you that are really into cameras, if you get wide-angle lenses that are old and very close to the sensor, sometimes they can cause color fringing in the corners. And that color fringing in the corners is literally the light not being able to correctly get into the hole it needs to get sensed and go out to the computer. It just doesn't get there. The walls here shadow it. So what we can do is, instead of fixing any of these problems, we can just cover it up with a little band-aid. And that little band-aid is something called microlensing. Microlensing is doing that lens that has no back distance again on top here. And with that, now the light comes in, turns the way we want it to, and goes right down into the sensor the way we like it, and maybe we lose, you know, a tiny little bit of the corner, but we don't have to worry about the majority of the lens. The majority of the sensor. The majority of the sensor does get light. So cameras that have very good micro lenses can handle incident edge light. Cameras that do not have good micro lenses on their sensors must have very direct light into the sensor, or you'll get strange colors in the corners or darker corners, right? Because this would also make the corner much darker in addition to messing with the color. So just realize that this shift is very important. These micro lenses, which of course is one of the things that isn't advertised very often in cameras, but can make an absolute world of difference for some specialty lenses, and especially very small, short those short lenses that we like to, carry around with us in our pockets. Right, there are two more peculiar ways to deal with the splitting of the three colors of light into sensible lights. One is called a Foveon sensor. Foveon. It's a brand name. And what that one does, I'm going to forget the color. It is green, blue, I think. Don't quote me on this. And then red. And each sensor acts as a filter. So this is a stacked sensor, and each sensor acts as a filter. So the green senses green and absorbs it. Blue comes through, gets sensed by the blue, and it absorbs it. And the red does the same thing, goes all the way through and absorbs it. The reason, actually, you know what, this is backwards, and I know why it's backwards, because we remember our basic physics. The blue is going to be first, because it's the most energetic, and it's easiest to trap. Green is going to be second, because it is slightly less energetic than blue, but more energetic than red. That's going to be the second one to trap. And then red is our last one, because the longest wavelength, least energetic, and hardest to trap. And that will give us our blue, green, and red of the Foveon sensor. So each one of these sends out its information to the computer like this, and it's a stacked sensor. This has not seen the level of development money and research time that the Cmos sensor has, but we may see some more development out of this in the future. I believe the only company that's using this right now is Sigma, and they're not a really huge camera manufacturer compared to everybody else, so this is a really interesting and cool way to do it. However, there's just not that much research into it. Also, one advantage with this is you're actually getting all three colors per pixel. Whereas, as I said, the other ones were RG, BG. So you have to think that for an RGBG, this gives you one full color pixel. Whereas if you have them stacked, each one of these would be a full color pixel. So you're actually getting more information in this sensor than you are in this sensor, but I think that just the limited development and the limited research dollars still just keeps this out of being more popular or easy to use than this one. So this is still the most popular. There's an absolutely absurd way to do this. This is a really cool method that nobody uses for cameras because it's just completely crazy. And that is using a prism to split your image. So we can have Prism. Have red. Have blue. And we can have green. Right, more energetic is going to bend more, less energetic is going to bend less. We can make a very, very fancy one of these that actually turns the light entirely. I believe it's called a beam splitter. Not that I know how the internal reflections work, but a beam splitter essentially takes your three-color signal in the front, that wouldn't be the way it would be. My terribly drawn one should at least be as correct as I can draw it. And our beam splitter essentially does this. Inside here there's enough prisming action where we can actually send them at 90-degree angles to each other, and then we can just put one sensor in front of each color of light. This you will see on older video cameras, and it is called 3CCD. This is the charge coupled device style. This is the older kind of sensor. But this is a way to do this splitting that does not lose light, right? We don't have any filters in here. It's just splitting the light as we go through and shoving it out to three sensors. So we do not have the loss of light that we have from filtering using the Bayer sensor, which was the one where they're all next to each other. So this one and the Foveon have probably very similar levels of light gathering capability for the physical. Right, there are two more peculiar ways to deal with the splitting of the three colors of light into sensible lights. One is called a Foveon sensor. Foveon. It's a brand name. And what that one does, I'm going to forget the color. It is green. Blue, I think. Don't quote me on this. And then red. And each sensor acts as a filter. So this is a stacked sensor, and each sensor acts as a filter. So the green senses green and absorbs it. Blue comes through, gets sensed by the blue, and it absorbs it. And the red does the same thing, goes all the way through and absorbs it. The reason, actually, you know what, this is backwards, and I know why it's backwards, because we remember our basic physics. The blue is going to be first, because it's most energetic, and it's easiest to trap. Green is going to be second, because it is slightly less energetic than blue, but more energetic than red. That's going to be the second one to trap. And then red is our last one, because the longest wavelength, least energetic, and hardest to trap. And that will give us our blue, green, and red of the Foveon sensor. So each one of these sends out its information to the computer like this, and it's a stacked sensor. This has not seen the level of development money and research time that the Cmos sensor has, but we may see some more development out of this in the future. I believe the only company that's using this right now is Sigma, and they're not a really huge camera manufacturer compared to everybody else, so this is a really interesting and cool way to do it. However, there's just not that much research into it. Also, one advantage with this is you're actually getting all three colors per pixel. Whereas, as I said, the other ones were RG, BG. So you have to think that for an RGBG, this gives you one full color pixel. Whereas if you have them stacked, each one of these would be a full color pixel. So you're actually getting more information in this sensor than you are in this sensor, but I think that just the limited development and the limited research dollars still just keeps this out of being more popular or easy to use than this one. So this is still the most popular. There's an absolutely absurd way to do this. This is a really cool method that nobody uses for cameras because it's just completely crazy. And that is using a prism to split your image. So we can have prism. Have red. Have blue. And we can have green. Right, more energetic is going to bend more, less energetic is going to bend less. We can make a very, very fancy one of these that actually turns the light entirely. I believe it's called a beam splitter. Not that I know how the internal reflections work, but a beam splitter essentially takes your three-color signal in the front, that wouldn't be the way it would be. My terribly drawn one should at least be as correct as I can draw it. And our beam splitter essentially does this. Inside here there's enough prisming action where we can actually send them at 90 degree angles to each other, and then we can just put one sensor in front of each color of light. This you will see on older video cameras, and it is called 3CCD. This is the charge coupled device style. This is the older kind of sensor. But this is a way to do this splitting that does not lose light, right? We don't have any filters in here. It's just splitting the light as we go through and shoving it out to 3 sensors. So we do not have the loss of light that we have from filtering using the Bayer sensor, which was the one where they're all next to each other. So this one and the Foveon have probably very similar levels of light gathering capability for the physical structure. The sensor, the electronics are of course a completely separate thing. Okay, so we kind of as a camera buying culture and technology set, have kind of decided on Cmos. We don't use the 3CCD. Foveon gets used every once in a while, but much more rarely. So to make a Cmos sensor better, and kind of what we talk about when we talk about better for sensors, is there's a few things that we can think of when we talk about better for sensors. It is resolution, right? How many pixels can we get in a specific area? Resolution. The other thing we can think about for the quality of a sensor is how little light, right? How few of our little photon friends does it take to get a signal? How few photons does it take to show a positive signal and say, yes, there is light in this spot, or there is not light in this spot? How well can we do with that ability? And this ability, how little light we can get into here, is something that you'll see on a camera is referred to as ISO. This doesn't mean anything. These letters are from film days. It is anachronistic to the nth degree. ISO is just a number. It doesn't even have that same relationship that like f-stop does. There are some mathematical metrics for it, but I'm not going to worry about them here. They're not relevant to what we're talking about. But what we can think about with those numbers is that they simply double, right? We can have ISO 100, 200, 400, so on and so forth. And these are a doubling of the sensitivity of that camera to light. So if it takes us 10 photons to set off this sensor, it'll only take 5 to set off this one. It'll only take 2.5 or 3 to set off this one. So as we double our ISO, we double our sensitivity. But there's a problem. You can't just freely keep bumping this up, because what happens is that sometimes these little pixel sensors, instead of getting a photon, don't get one and think they see one anyway. What that is that's called noise. It's noise in the image. When you hear it in audio, it's static. It's that like noise in the background. It's unintended signal. So when one of these pixels goes off and says, yes, I see light, I see, whatever amount of light, and it didn't, right? There was no incoming light. That is noise. When this bumps up, the chance of this happening also bumps up. So the higher our ISO is, the more likely we are to see fewer photons, but the more likely we are to have false positives as well. This gives us kind of a grainy or snowy look to an image. We get lots of little dots here and there of really bright colors or of just white. And that is these individual pixels failing and reporting light where there is none. So ISO is nice. We can bump that up so we can see in lower and lower light, but we get noise. Sorry, that's not an N, it's an M. But we get noise out of the back of it. So we get all this snowy effect the higher this goes. A higher quality sensor can give us less noise at the same ISO. So a camera 10 years ago at ISO 400 might look like a camera now at ISO 24,000. And that's just because, or 25,600, whatever it is. And that is just because the sensor has gotten better at reducing noise and better at sensing incoming light. There's another way that we can do this that's actually counter to resolution. So all of our cameras have a certain size sensor. if I have a sensor that's this big, that's 1 pixel, that's a really big sensor. It's great, captures a lot of light, but 1 pixel isn't super worthwhile, right? That goes back to our little creature right at the beginning that can only see whether it's light or dark outside. It's not useful. If I go to this, well, that's nice, right? I get 4 sensors, but I only get 1/4 the amount of light. Do that again, and again, and again, and again, and again, all the way down to having very small sensors, right? The sensor in your cell phone is about that big. Yeah, there's my finger for scale. Sensor in your phone's about that big and has probably, again, 12 to 36 million pixels on it. That's a very, very small amount of light hitting each one of those dots. So some cameras that are shooting for very low noise actually go with a lower megapixel count, because instead of having these, if I go with a lower megapixel count and make this all 1 pixel, well, then I can capture more photons there, and I have a better chance of not getting these false positives because I can be more sure that the signal I'm seeing is a real signal from up here. So we can reduce the resolution to improve noise. Technology has progressively improved noise. It's progressively improved how high we can go on our ISO scale. But do realize that resolution and noise can be counter to one another sometimes. Oftentimes things with lower resolution of the same generation, of the same technology, will have lower noise than higher resolution cameras of the same technological level. Some cameras, in addition to having their on sensor, right, we talked about Cmos cameras having little amplifier that lives on the pixel. In addition to this, we have some cameras that have their on sensor amplifier, then it goes out to a secondary amplifier at the corner of the sensor, kind of like a CCD camera, but by doing both of these amplifications, you can get a very high ISO with very low noise. So this is double or 2-stage amplification, and the A7S series has these. I think there's a Canon that has it, and I think there's a Nikon that has it as well. So if you want to shoot in the dark, you want a camera that has this double amplification feature, or it's at least a benefit. You can do it without it. This helps. So realize that there are some other little tricks that we can use. You can also use those micro lenses. Can help pull light, right? If you have a pixel that's only this big, and you can use this to capture more of the light into that pixel, then that gives you, a little bit more light for the size of the pixel. Of course, when you're comparing that to resolution, you can only go so big on this before your lens is inside the next pixel. And that doesn't help, right? If this lens goes to here, then this one can't have as big of a lens, and you start to cause problems. So micro lensing can only really help you so much there. Now let's talk about the way that digital cameras read out their sensors. So if I have a digital camera sensor, let's do 4 lines for a sensor, 4 columns for a sensor. If I have a sensor that looks like this, what happens is I take by taking the image, is I blank this sensor, I bring that shutter up, I open the shutter, I close the shutter, and then I read off all this data. Well, the way that I read this data is that these actually cannot store information in and of themselves. So the way that they do it is that they read out immediately to a bit of memory on the end of each line. Bit of memory, we're going to put a little M here. They read out that data to the end of the line, but they cannot really store data within themselves. Then what happens is all of these memory chips at the end, these guys all read out in order. 1, 2, 3, 4. And by doing that, we get a sequential read. This is 1, this is 2, this is 3, this is 4. Now, if you have a physical shutter, this is fine, right? Because it's dark in here. We don't need to protect the sensor at all. We can read these out in order. However, if it's like our phones, or if we're using electronic shutter, right? Electronic shutter. If we're using an electronic shutter, like the ones on our phones, again, that doesn't have a physical shutter. The problem with doing it like this is that we get something called a progressive scan, where we are scanning essentially each pixel as it goes down. You may have seen photos online of like a propeller on an airplane where it looks all wobbly. That is because we are reading these in order, and this is actually happening at a different time than this is, at a different time than this is, at a different time than this is. And when you go down, thousands of lines, that becomes an appreciable amount of time. For most sensors, it is between 1/30th and 1/60th of a second. I think the most advanced basic electronic shutters are about 1/90th of a second. I think the A7 is something like or the A9, whatever, is 1/90th of a second, something along those lines. By the way, this video will age very poorly because technology changes. But yeah, so we're getting about these ranges. So you have an appreciable amount of time, top to bottom, on here. Actually, if I wobble this, you can actually see it wobble. Like there's a jello-y sort of, let me fix this. There's a jello-y sort of wobbliness, and that jello-iness is it reading top and bottom kind of differently. And on this camera, I believe it's 1/50th or 1/60th of a second. So the wobble, you can actually see my arm is straight, but see how it looks like it's waving left and right? You're actually seeing this scan top to bottom on this sensor. So yeah, so this can become a very, very big issue, especially when recording video. If you see like jelly, especially when you pan, that's what you're seeing. There is, however, something called a global electronic shutter. And these are only in heinously expensive cameras, like really stupid expensive cameras. And what those do is those just put a little bit of memory on each pixel. Put a little bit of memory on each pixel. That way, you can just expose everything at the same time, be patient, and then dump everything in order from images that were essentially taken all at exactly the same time. So instead of taking all these, then all these, then all these, then all these, every little pixel essentially takes its own picture, stores it, then sends it on, but the timestamp on that initial take is the same. So by doing this, you get a really, really clean image. You don't get the wobble, and you don't get the scan. The problem with this is that putting memory on each one of these pixels is insanely expensive, thus leading to the cameras being insanely expensive. But this will come down in the future. I am very much looking forward to having a global electronic shutter camera. Now, we have our pixels. Get rid of them, and I want to talk about backside illuminated sensors. So, let's say we have a 1 pixel, or one little pixel friend. Him being bigger allows us to capture more light. We've already talked about that. Now, when you make a circuit board, you can actually really only do that on one side. You can do it on both sides, but it's a huge pain. So think about it on one side. We need to have our sensor. We need to have all the electronics to take all that information from our sensor and send it to the end of the line. We need to make sure that it can get power. So we actually have a lot of stuff going on that needs to take place in this. So what you do is, instead of using this whole area as a sensor, so you take a chunk of the bottom of it, and you say this is going to be our wires that go out. Right? And it's probably actually more than this. You take the wires and you go out. And then that goes down to the end of the row and tells the camera what this pixel saw. But it takes up a chunk. So now we're not using any of this area to get light. We're just using this area. You can use micro lenses to fix this a little bit, but it doesn't fix everything. But we're using these lines to get information out. Now, here's the rub. If I make a smaller pixel, there's a minimum size for these wires. These wires actually have to be the same size. It can't be smaller for a given technology. It can't be smaller. So now this little pixel only has about half the light gathering that it should, right? These aren't doing anything. These are just taking stuff out. They're not helping. So this is actually like our eyes. Remember, all of our eyes, we have sensors, and then all the nerves and all the veins and everything are actually on the front of our eyes. You can look in your eyeball and see it. So our eyes actually work very much like this. They take the information, and that's on the face of the sensor. It's not hidden behind the sensor. But we can do something new. So these, having the wiring on the front really messes you up on small sensors, right? On bigger sensors, it doesn't matter so much because you're not taking up as much of the area. But what we can do is something called backside illuminated sensors, and this is a circuit board that is screened on both sides. So we actually have electronics on both sides. So what we do on that is on the front, we actually run all of our wires right down the center of the pixels. It doesn't matter if it's in the center or not. Then on the back side, we scribe in our pixel on the back side and run our cabling through. Well, it's not cabling, but we run our conductors through the surface. This gives us much more surface area, because remember, on the back side, we're just seeing this. We're not seeing those wires. The wires are on the back side. But this is a relatively new technology. iPhones had this maybe 5 or 6 years ago. By relatively new, I mean like in the grand scheme, not new for technology. But we can have these much bigger sensors for the wires. Again, it's less important if your sensor size is already big, but if your sensor size is tiny, this is like magic, right? We just doubled the amount of light that we could get into a sensor just by flipping around the way that we wired the thing. For bigger sensors, it makes a little bit of a benefit, and it's definitely good, but it is not as important as it is for smaller sensors or higher density sensors. Again, our eyes have it on the face. Our eyes are like this. We have all our wiring on the front. The octopus eyes have the wiring on the back, like backside illuminated sensors. I just find that very odd. So another thing we have with sensors is dynamic range. Dynamic range is the ability of the camera to see both light and dark at the same time. I know that sounds very strange, but dynamic range is how bright versus how dark can the camera make one-step differences. Older cameras, if you wanted to see down here in the shadows, you might have to cap out your brightest whites right there. And then as this dynamic range improves, it allows the camera to see these tiny steps at greater and greater distances from one another. I believe that most cameras exceed 14 stops dynamic range, and stop just means double. So it's 14 doublings of light between the darkest and the lightest differentiation. It's not the darkest and lightest thing that you can see, right? Because you could just point your camera at the sun and hold a card in front of it, but it would blow out. You would not be able to see the difference between these two. It would just be completely white and completely black. What we're interested in is how much this tiny little differentiation is. And for that, we're looking at dynamic range. It is the step at the end of the spectrum. So if we're exposing for really different environments, if all you're shooting has really good lighting and is very like gray and neutral, then this doesn't matter at all. What this matters for is situations where you have ultra bright lights and very dark areas in the same shot, and you need them to both look good. So for that, we use something called dynamic range, and that is just how good that little sensor is at picking up photons, right? Because if you can pick up one photon, you can get this very nice little step. If you can't, then you might have to drop the range to something shorter than your overall full range. So dynamic range is something that's very important. Again, shadows to brightness, and it is generally given in this increment, some number of stops. More is always better. I don't think I've ever seen a situation in which more was not better. But yeah, so this is a very useful thing. Realize that dynamic range does change with ISO. We talked about ISO being the sensitivity of the sensor, of the little pixel. As this goes up, dynamic range is going to go down. Sometimes there are cameras that have a dynamic range that kind of looks like that, where the highest dynamic range is not at 100. It might be at 400 to 1600 range, and then it's going to pretty much come off a cliff on the other side. But realize that they're not always straight down. Sometimes they will peak and then drop, and this is oftentimes in those cameras that have dual amplifiers in them. But dynamic range is rated like this. If you expect to shoot at these ultra high ISOs, you can actually find this chart for every camera. So if you know you're going to be shooting like basketball, which is very relatively poorly lit, without having a super nice lens, then you may want to look and see, if I'm at 32,000, does the dynamic range fall off a cliff like that, where I'm down here? Or does the dynamic range just fall in a linear way where this will be okay? Or can I find a camera that peaks closer to where I need it to peak? So realize that dynamic range is this number, but it does have this graph. If you're really interested, you can always find these graphs for dynamic range of a given sensor, and that is the sensor in the camera. So this is a very abstract look at cameras and the way cameras work, and it seems one of those things that it just doesn't matter for the purposes of using a camera. But the nice thing is, from these basic principles, from these basic ideas, you can then extrapolate forward to, why is this camera better than that camera? Why is this lens better than that one? Why does that person's photographs look like that and this person's photographs look like this? From the taking standpoint, of course, you can mess with them as much as you want in Photoshop and things like that, but from in camera, this gives you some of those basics that you can then work forward on. You can also take some of these things and keep looking into them, right? Most of these things I have actually very much glossed over the functional scientific way it works in order to get it down to even the absurdly long time that this video has been running for.